Hello once again. We're moving on to chapter 4 now. Now, the first problem in chapter 4 covers a pretty simple setup. You have a reservoir, it's at a constant temperature of 373 degrees Kelvin, and in contact with this heat reservoir is some amount of water. It's Saturday. People love riding outside on Saturday afternoons. Go watch the baseball game or something. I don't know. Anywho, we have some amount of water here that's held at 0 degrees centigrade or 273 degrees Kelvin. And part A of this problem asks us to solve for the change in entropy of the water, change in entropy of the reservoir itself, and the change in entropy of the whole system. Now, part B asks a similar question in the sense that it wants to know the change in entropy specifically. Oh my God, that's terrible. I should not teach Greek. Of our whole system with these two reservoirs. And we're basically trying to see, like, is it different, is it the same, so on and so forth. Anyhoodles, if we want to begin with the first equation, or the first problem, we need to evaluate an integral. So, from the second law, we know that the change in entropy is greater than an integral of the change in heat over the temperature. Now, we don't know anything about the change in heat dq necessarily. We don't have like some scalar quantity that can tell us what this is. But what we do know is that we can write our heat as being the mass of whatever the heat of our object is, times its specific heat per mole C, times the change in temperature delta T. Now, because this is a differential form, we're going to say that dq, that's what I like about Texas, is equal to the mass of our object times the specific heat again, dt, because we're integrating. So what we do is that we substitute this variable m for our dq, and then we can integrate over a change in temperature for our water. So that becomes ds is greater than or equal to, specifically, the integral from our final temperature, which is 373, to 273, or 273 to 373, I need to be specific in my language, of the mass of our water times the specific heat per mole of our water, dt over t. Now we can integrate this. These are constants, so we can just pull them out. Forgive me for writing them in the wrong order. H2O, just so we're specifying that it's waters. And then when we integrate dt over t, we get a natural logarithm of 373 minus 273. So when we evaluate that, that's actually, I'll just show it expressly. So I'll have 373 minus natural logarithm 273 is equal to m H2O C of the natural logarithm of 373 273. And then from first observation, we know that this particular integration was done properly because this value will be greater than 0. Natural logarithms whose arguments are greater than 1 are, well, resolved to some scalar amount that is also greater than 1. So we know that this is good. So we hang on to that quantity, right? Now for the reservoir, it's a little bit different. The reservoir isn't changing its temperature. So in order to evaluate this dt term here, we have to handle the entropy a little bit different, right? So the way we handle this one's entropy instead is we note that we know we have a change in temperature, right? But we're looking specifically at the reservoir. So delta S is going to be the mass of, once again, our water, because we don't know the mass of the reservoir, but we know the mass of the stuff that we're actually changing the temperature of, times the specific heat of the water, because we don't have material for the reservoir. It's just some heat reservoir giving off heat, but we are changing this object of water, so we have to use it. And then we incorporate how much heat, or how much temperature is changed of the object we're heating up. So, oh my goodness, 373 minus 273, which is just 100. And then we divide that by the constant temperature of the reservoir, being 373. So now we have two terms that we can use to add together to get us delta S for this whole system. So our delta ST is going to equal to our delta S of the water plus the delta S of the reservoir, which whenever we do this math out, and I think I included some extra decimal points when I did it. Oh, I didn't evaluate it here. That's fine. Oh, wait, did I? Hold the phone. I'm just looking at my notes. No, I was lazy. I didn't write it down. But you can throw this into a calculator, and you'll get your answer, regardless. For part A. Now, for part B, we need to look at it in terms of taking our water, we heat it up a certain amount, and then once we've heated it up a certain amount, then we extract it and then we move it to a different reservoir. So I like to do this sort of visual. So let's say we have our reservoir here, and here's our water. Looks like a kidney bean. Weird visual, but it always helped me. So that we take it and then we just get a reservoir too. And so here's our water again. So this is after we increase the heat, we transfer some amount of heat between these two reservoirs onto the other one. The way we handle this is that we need to handle first the change in entropy of the water, and then we need to handle the change in entropy of this first reservoir, and then the change in entropy of the second reservoir. And the way we do that is we basically repeat the same process. Our change in entropy of our water is going to be the result that we got last time, right? Oh my heavens. Delta S H2O. It's still going to be MC natural log 373, 273. Because entropy is whenever you're doing the integration, I believe the term is path independent. So it doesn't necessarily matter that you've taken this and then shifted it over to a different reservoir. You could break this into 3 reservoirs, 4, 5, 6, doesn't matter. You're still ultimately getting it from some initial temperature to some final temperature. So when you do the integration for each of those subsequent transfers in between reservoirs, you're going to get the exact same result regardless. So this stays the same, which means that our change in the entropy for our reservoirs, so let's do change in S of reservoir 1 is going to be, once again, the mass of the water, specific heat of the water. Then we need to take into account the change in temperature for that particular reservoir of the water. So this would be from 323 minus 273, because we're only changing an amount of 50 degrees. And then this would be over 323, I believe. Forgot something. That needs to be minus, because the reservoir is losing heat. Dolly. Heat's going in. Heat's going in, so the reservoir is losing heat. So make note of that in the previous calculation too. This term will be negative because it is losing heat. So these two are also going to be negative. We're going to repeat the process for the second one, so we're going to get minus MC, but we're going to do 373 minus 323 divided by 373, because that's the constant temperature of the second reservoir. And then we just sum over all of these. And then once we sum over all of these, we'll get an answer again. And it should obey the fact that our change in entropy will be greater than or equal to 0. It should obey the second law. If you don't get this result, you've fudged some of your numbers somewhere.